we'll start again. I'm sorry for going over time on the first lecture, but we can. I'll try to save it by starting what should have been your break. And this would be a quick tour through hearing of mammals, reptiles, and frogs in 20 minutes. So if something is skipped, you are feel free to ask in the break or so about what's going on. So we'll look at the ears in these groups. First of all, what does we've looked a little bit at the middle ears, compared the middle ears. What does the inner ear look like, where the action is taking place, so to speak? If we look at representatives here, here's a lungfish, here's a frog, here's a bird, and here's a mammal. And what you see immediately when you look at these inner ears is that the upper part is very similar. That's where the organs of equilibrium, which sometimes are called the vestibular organs, are sitting. These are the ones that detect the motion of your head and whether you are pointing up or down. Very useful things. They are conserved in almost all vertebrates from back to the at least back to the lampreys or so. So the action when hearing is concerned is always taking place in the bottom of the inner ear, and that's where the lungfish, they have an otolith like in the fish system. The frogs have a couple of hearing organs sitting here. We'll talk about those later, and a large otolithic organ that responds to vibrations. The birds and reptiles have an auditory or basilar papilla here, which is where the hearing the sensory cells are sitting in a macula here. And then, of course, the mammals have the coiled sensory epithelium, the cochlea, which you can see as a space-saving way of having a long basilar papilla, right? So mammals generally have sensitive hearing. And they have got this sensitive hearing by evolving three fundamental new features that are not really found in any of the other eared animals. One is the pinna, or the external ear, more important in terrestrial mammals than in aquatic mammals. And the other one is the three-ossicle middle ear, the two extra middle ear bones, which evolved through a complicated transition of some small jaw bones into the inner ear, which I unfortunately don't have time to go into, but you can ask about it. And then there's a high frequency, extended high frequency sensitivity simply created by having a very long sensory epithelium, which is elongated in the specialized cochlea. And the cochlea is really specialized. It has a group of cells that are not sensory hair cells, but are used for cochlear amplification. If you look at the processing in the CNS, there are not that big differences. Of course, there are differences in the echolocating mammals, but compared to the other tetrapods, it's not that different how the nervous system is working. I put this up here. This is a collection of some land mammal audiograms, and I put it up here to alert you to this page, which is a gorgeous page if you want to to know anything about mammal hearing. So this is created by two researchers at the University of Toledo, Henry Hefner and Ricky Hefner, and they have done psychophysics behavioral audiograms on a variety of mammals, many more than are on this curve. One of the claims to glory is that they're the only ones that have made audiograms of an elephant. And what we know about elephant hearing, more or less, is based on their audiogram of one Indian elephant in the zoo. And that is for shame. Something should be done about that. But they have also made cows and deer and so on. So there's some interesting stuff if you want to know something about how antelopes or buffalo and so on are hearing in this database here. But what you generally see is that mammals, and I don't know if you can make out the colors, but this is us. This is the humans. Mammals generally have the same kind of hearing. It's fair to say. what the changes are mainly effects of size. So big animals generally shift the hearing to lower frequencies, small animals to higher frequencies. And then there are some special weird features. Here's a bat. And this is a special kind of bat. This is a bat that emits a constant frequency, a constant ultrasonic frequency, and where its cochlea is specialized really in the region of that frequency. So it's called an acoustic fovea, and it shows up in the audiogram. So it's especially sensitive around the frequency of its CF core. So these are mammal audiograms, and the basic functioning of mammal ears are it's very similar across mammals. There are a few exceptions that we can talk about in the break, like golden moles and so on, that have a very different middle ear, but I don't have time to talk about that. So the structure of the land mammal ears are generally similar, and as a model of how that ear looks, we can use the human ear. It's a pretty good model of any mammal ear, and it's of course it reflects the ear has the three divisions: the external ear, the pinna, the middle ear with the ossicles and the eardrum, and the inner ear where the sensory organs are sitting. So here you see a sort of a diagram of that. So the pinna, the external ear, is, as I said, a special invention of the mammals, and it has several functions for the mammals. It provides a gain because it acts like a horn, so it sort of collects energy. Like the tympanum does, it collects even more energy by being funneling sound into the tympanum. It can filter the sound. It can give us some directional cues because the sound coming into our ear canal will be different whether it comes from the back of our head or in the front of our head because of the pinna. And then, of course, some mammals can actually, and we can to a very small extent, they can move their pinna. So if you look at an impala, for example, in the sound, you will see that it's actually turning its ears towards the sound source, and thereby getting even more sound energy. One wonderful example of it too is the bat-eared fox. If you see a bat-eared fox hunting, you will see that it actually focuses its ears like this. And that's also an animal we don't know anything about it here. And then we have the middle ear. The special feature, that's a crummy slide, I apologize. The special feature of the mammalian ear is the three middle ear bones. So outermost at the tympanum we have the hammer, then we have the anvil, and then we have the stirrup, the malleus, incus, and stapes. The stapes is homologous to the middle ear bone in all other tetrapods, and that originally was a kind of a brace or a unmovable element. And these ossicles, they scale with size. So here you see them from a very small animal like a bat, rat, cat, wolf, horse, grey seal, and Indian elephant. So there's a huge scaling with size, and that is what also defines the frequency sensitivity. So if you have a huge middle ear like an elephant, a huge ear like this, then it will lower the frequency of what you can receive. And conversely, if you want to hear ultrasound, you would want to make these elements as small and light as possible. So there's clear effects of scaling here. And the seals are a weird example of mammals, and how exactly that ear functions is a puzzle to me, but we can discuss that another time. So what is talked about when you talk about the middle ear is often impedance matching, and that's a really bad term because it sort of implies that the ear is matching the impedance of the liquids in the inner ear to the impedance of air, and that is not possible. The only way you can have the same impedance of air is to have something that has the same density as air. But the idea of the ear is to make of the middle ear is to make as big a splash as possible, to compensate for the loss you have being in air because you have a reflection of sound you have something that collects energy and funnels it into the fluids of the middle ear to making it as big a splash as possible, as I said. And the idea of having a middle ear gives you generally a 30 to 40 dB increase in sound level, in sensitivity. The inner ear, the cochlea, as I said, combined of an upper part, which are the organs of equilibrium, and a lower part, which is the actual sensory organ, which is a long tube with two chambers that are connected. So when you stimulate the stapes, you make a fluid movement in the oval window, and the pressure goes out through the round window. This sets up a special kind of thing in the mammalian ear called the traveling wave, and that occurs because this membrane here is not uniform, but it's very thin and stiff in this end, and it's very broad and sloppy at this end here. And these simple mechanical differences creates a frequency analysis here. Because if you stimulate it with a high frequency, you will have a maximal amplitude in this end, and if you stimulate it with a low frequency, you will have a maximal amplitude in this end. So that's the basis of frequency analysis by the cochlea. So you make a splash from the oval window, and this hydrodynamic wave is translated into, depending on the frequency, is translated into movement at different places. And actually, if you make a rubber membrane with the same dimensions, with the same properties, that will exhibit a traveling wave too. So this is purely mechanical, and that's a special feature of the mammalian ear. So actually it's quite simple. So if you have a line of sensory cells here, the high frequencies will excite the sensory cells that are sitting here, and the low frequencies will excite the sensory cells sitting here. So that's the basis of it. But it turns out that the ear is more complicated than that, because there are several rows of hair cells. So there are the inner hair cells that are sitting here, and the outer hair cells that are sitting here along the basilar membrane. Interestingly enough, we only use these ones these are the only real sensory cells. And the function of these other cells are cochlear amplification, and that's again a mammalian speciality. So these cells here, when they get stimulated by the mechanical traveling wave, they do an extra thing. They do an extra twitch, and that extra twitch excites the real sensory cells that are here. And how exactly that is happening, we don't know. But it has implications. For one thing, it gives mammals a much bigger sensitivity than they would have if they had lost this apparatus. So they gain about 50 to 60 dB, so up to 1,000 times higher sensitivity. But the other thing is that this is a real weak point of the mammal ear. If you're looking into damages by noise, the first thing that gets damaged are these sensory cells here. And that's a very typical and characteristic hearing loss. So now you know all about mammal hearing. Now we switch to reptiles. And reptiles is really a group that shouldn't exist. It's a paraphyletic group, meaning that it's a ragbag of animals that are not mammals or birds. Amniotes that are not mammals or birds, and really, if you look at them, this is a correct relationship. So what happened when the amniotes, the animals that have developed a terrestrially adapted egg with different membranes that protected it from desiccation, when they first occurred, the first lines splitting out were the ones splitting out to mammals, and you have some of the wonderful examples of this line from the Karoo. You know the cynognaths and the dimetrodons and so on. These are branch offs of the line leading to mammals. Of the other ones, the next one splitting out was the line going to the lizards and the birds and crocodiles and so on. The lizards and the tuatara form a separate group. The turtles, the birds and crocodiles form a separate group, and the turtles have been kicked around by the taxonomists, but have now probably found a good sweet spot here as a sister group to the birds and crocodiles. But that also means that if you want to treat the evolution of the function of ears, you should really treat these groups separately. You shouldn't think that there are some communality to them because they're reptiles, because they have evolved separately. If we look at the lizards, they have generally a very sensitive tympanic ear, and if you measure their hearing, and we've measured these using auditory lobe potentials that I'll talk about after lunch. If you compare them to unspecialized birds, this is a budgerigar, that's one of the lines, that's this line here, and a screech owl, this is this line here. And here we have the symbols are an owl and a gecko, and you will see that they are pretty much similar. And they have so they have a very sensitive ear. This is recent things that Catherine and I and Michael Cherry did out in Kuruman on barking geckos. And again, you see that they have also a fairly sensitive ear. You should know that these are ABR measurements or evoked measurements. They're usually 20 dB above the real threshold. So we expect that the real threshold is probably down here. So that's a quite sensitive guy. These guys are sitting and calling in their little burrows and probably really have a very good hearing. And then there's this feature about lizards that you can actually shine a light through the head of a lizard. And that shows you that the middle ear cavity or the mouth, everything is completely transparent. And for sound, that means that sound with very little loss can go through the head and reach the tympanum on the backside, so to speak. And that means that these two sound waves, they can interact either constructively, so they add up, or destructively, so they cancel each other. And that is dependent on their phase, and that is dependent on the direction. So this ear becomes strongly directional, and actually is one of the most directional ears known is the lizard ear. But we know very little about what they're actually using it for. That's why we are going to Kuruman and working on barking geckos, because that might be the best example of a lizard that actually has a measurable acoustic behavior. Snakes, snakes do not have a tympanic ear, and that is because they have instead connected their columella that you see here to one of the jaw bones. So the inner ear is directly connected to the underside of the jawbone, here. And the idea of this is probably to be very sensitive to ground vibrations. So the ground vibrations are transmitted directly into the inner ear by this thing here. They also do show sound sensitivity, but that's we measured that a while ago, and that's probably just because the head is being pushed by the sound wave. So if you measure the vibrations of the head, then you can directly correlate the vibrations with the induced vibrations with the sound sensitivity. But of course, you find a very nice vibration sensitivity. This is vibration sensitivity on this side. This is sound sensitivity on this side, and it shows, and it's probably illegible down there. But this is a python. This is a rattlesnake. And the real master here is the place, a place for some odd reason that I don't know. but they stand out compared to other mammals like the salamanders or the spiders or for example lungfish. They are up here. And of course, if you look at sound sensitivity, they're quite insensitive. So we are up here at around 80 dB for the royal python that we studied. The rattlesnake is about here. You should note though that this is again an ABR measurement, so should probably be lowered by 20 dB. So then it would be almost the same for the python and the rattlesnake. But that's what you lose by specializing your ear for vibration sensitivity. The tortoises and turtles, again a special group, a separate group that is the sister group of the archosaurs, have a tympanic ear, and the turtles, at least one turtle and probably one freshwater turtle like the slider, which is the only one we have studied, and sea turtles appear to be adapted for underwater hearing. But the ear is quite similar in the aquatic turtles and in the tortoises like this one. So what you see is an eardrum, which you can see here out on the surface, a very long columella, a middle ear bone, and then interfacing with the inner ear through a middle ear cavity. Things in the radiate slider is a little bit different. They have very, very large middle ear cavities. These are the middle ear cavities you can see here. And then they don't really have a visible tympanum, but they have a tympanic disc, which we think are some of the adaptations for underwater hearing. And I'll be happy to talk more about that, but you can ask later. But anyway, if you look at audiograms of turtles, you see that they have quite low frequency hearing. They have a very short basilar papilla, a very short sensory papilla. And the peak is generally about 200 to 500 hertz for the land turtles. We very recently did two tortoises. This is the red curve, that's a red-footed forest tortoise, and the blue curve, which is an African spurred tortoise, but a baby. It was only this size. They grow to this size, of course. So we haven't yet gotten at the real big ones. But here you see the audiograms, and for comparison, this is the slider, the radiate slider Trachemius, which is much smaller than these ones. So you see a sensitivity of a fairly good sensitivity of the ear. So again, this is auditory brainstem recording. So the real sensitivity is down here, about 20, and a low frequency sensitivity. Sea turtles, there's quite an interest of sea turtles, also of course for conservation purposes. And so I'm just, even though I'm not doing much with underwater sound, here are responses, different audiograms to underwater sound. So the full curves here are different species of sea turtles, and the dotted line here is a radiate slider underwater. Right? So, but again, I mean, they have a fairly respectable sensitivity to underwater sound in the low frequency range, and that means that they would also be vulnerable to underwater noise exposure and blasting and pile driving and so on, probably. And the reason for this is these air-filled middle ear cavities that would respond to the sound pressure. The crocodilian ear is very similar to the bird ear. Actually, except one feature, and that is that the crocodile and alligators, they have an ear lid, so they can close up their ear when they are in water. And the best sensitivity of those we measured was around 1 kilohertz. That we haven't measured a big crocodile, which would be an interesting experience, but these were alligators about this size. Yeah. But the function will be very similar to the bird ear. What time is it, Ole?
It's 10:30.
Okay. Quickly through the frogs, which is my animal, so I'm doing a terrible job on them. They have a tympanic ear, and you see a sketch, a diagram of it here. Here's the tympanum, here's a middle ear cavity, here's a columella, a middle ear bone. But the amphibians, in addition to having the middle ear bone going into the inner ear, have an extra element that can move, called the operculum, which is connected to the shoulder blade, to the scapula, and is an alternative route to vibrations to get into the inner ear. animals like xenopus have special adaptations for underwater hearing, which you can ask about if you want to hear about. The sensitivity of frogs is a little bit lower than the lizards, and that's because of the eardrum is not quite as thin and delicate as in lizards. But they, of course, can hear. Most of them, as you know, communicate with sound. Almost all frogs communicate with sound. And they analyze this sound by their two inner ear auditory organs, which is the amphibian and the basilar papilla. So generally, if you look at an audiogram, and here's an audiogram of an American tree frog, you will see two peaks. This is the sensitivity range of the amphibian papilla. This is the sensitivity of the basilar papilla, as it's called. And if a frog has a high frequency call, the basilar papilla will generally be tuned to that call. So if an animal has calls at 4 kilohertz, the sensitivity, it will have a sensitivity peak that is caused by the basilar papilla. So just to end it here, because this has been a reason, as I said, a very kaleidoscopic tour through a lot of animals. This is just to show you the importance of a tympanate ear. So these animals here are tympanate species. This is a toad, Rhinella, and two lizards, Anolis and Gecko, and the turtle, the red-eared turtle, and the alligator. This is the alligator. This is a turtle. And all these are animals that, in the course of evolution, have sort of lost their middle ear. And you can see that comes with a cost, right? So these animals generally get less sensitive. And one of the interesting questions in evolution is, why the heck did this happen? And that's a topic for another talk. So I'll end here. Questions? Yes?
Maybe you explain that how do you get the audiogram? Like, you measure the behavioral response to
No,
sound?
mostly, well, you could do that too, and I'll talk about it after lunch. But what we do is to make auditory evoke responses. That's a quick and dirty way to get audiograms. And you can do it even in lungfish. Who would like to train a lungfish to report the response to sound, right? But we could actually measure its hearing with the auditory brainstem response. Yes?
You were saying about the sensitivity to vibrations earlier. The place was quite unusually lower.
Yeah,
Do you know? Is that because it looks like demersal fish versus pelagic fish? And if they're the more demersal species, they're actually looking for sensitivity and vibrations in the seabed.
Yeah,
that would probably be evolutionary, and then other kind of demersal fish is the same.
It could easily be that it's specialized to listen for vibrations. As far as I know, these animals don't have a swing bladder, so they have fairly poor hearing as such, but they're probably better at vibration pickup.
Yeah.
Cool.
Yes.
I'm going to get in the eyes. Because we're a really mixed group in terms of backgrounds, can you throw me up one of your audiograms, please? Pictures. Are you going to do it? All right.
Like this?
Okay, Ole's going to do it. I'm going to ask you in really straightforward terms to walk through how you interpret an audiogram, but Ole is on it. So
you want to go there? Okay.
Because it won't be intuitive to a lot of people who
okay,
have got that background.
Yeah, cool.
Awesome, thank you.
Okay, you're going on.
In my talk.
It is cool.
Yeah, you're talk. But all, you need to be on the Google thing, or you need to give me, you need to run it from my computer.
Well, if we want to run it without any,
What?
I mean, there are sounds and so on.
Yeah, let's poor Kat, but if you...
Does she need to listen to this?
What's that?
Does she need to listen to this?